This is an introduction to matrix methods for linear systems. And we're going to revisit the interconnected tank problem where we had two fluid tanks containing brine solutions and they were connected and pumped, so the amount of salt in each tank was depleted. So basically this was the model that we had. From the interconnected salt tank situation. And the matrix method or algebra provides compact notation for expressing systems. So let's just take a look at this example that we had here. This right-hand side right here and right here, the right-hand side of each equation has a structure that's very familiar to something called the dot product. And actually, I wanted to put that right under here. And let's go ahead and see what we have here. So we could start with negative 4x plus 2y. And we have that equal to negative 4, 2. That matrix with one row and two columns. And that's the dot product with this vector x, y. Similarly, we have the second equation, 4x minus 4y, and we have the vector for negative 4 and its dot product with the vector x, y. So when we have an array of dot products, we then have what we call a matrix product. And of course, this is through matrix algebra. Basically, this is an arrangement of a set of dot products. Let's write it like that. So we have negative 4, 4 to negative 4. And here we have an m by n array. And this is in a matrix. And then we have what we call a column vector. Then that's where we have the dot products of the rows of the matrix with the vector. So let's finish that up. So we have that this is equal to, and we'll show that dot product. So as you can see, using matrix algebra, in this case, the matrix product is just the set of dot products. Okay, so now let's take a look at what we have. So we have m rows, and we have a vector with n components. And then we have the dot product of the two n-dimensional vectors. So now we have this product, and we could say now that if we had n columns, you can see that we would have this entire first row multiplied by that entire vector with n components, and so on and so forth. So basically, you could see that the dot product of two n-dimensional vectors is computed like this. So you would have a1, a2, dot, 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 all the way to a sub n, and here's our dot product with our vector row, x sub 1, x sub 2, all the way to x sub n, and we now have a1 x1 plus a2 x2, and so on and so forth, all the way to a sub n x sub n, since our vector has n components. So revisiting our tank example here, our interconnected tanks, we can write that system. So that tank system was dx dt is equal to the negative 4x plus 2y, and we had dy dt is equal to 4x minus 4y. So now we can write that tank system with matrix product notation as x prime y prime is equal to negative 4, 2, 4, negative 4, multiplied by the vector x, y. So let's go ahead and try a few examples. In our first example, we're going to express this system of differential equations in matrix notation. So rewrite 7x plus 2y as 7, 2, there's our vector with the dot product of vector x, y, and we also write 3x minus 2y like this. And then what we have is 7x plus 2y, 3x minus 2y is equal to the matrix product 7, 2, 3, negative 2, multiplied by xy. So in matrix form, our given system is the vector xy prime is equal to 7, 2, 3, negative 2, multiplied by that vector xy. Okay, let's take a look at our next example. And I do want to mention that this is given in normal form. And we can say that this linear homogeneous system is in normal form. Okay, so let's go ahead and write our system in matrix notation. So we will have this vector x1, x2, x3, x4, and we will have the derivative of that vector is equal to, and now we're going to line up our coefficients. So for x1, x2, x3, and x4, so we have 1, negative 1, 1, negative 1. Now we are going to have this vector x1, x2, x3, and x4. So we'll have that dot product, this multiplied by this. Let's keep going. So our coefficients in our second row are 1, 0, 0, 1. We have root pi 0, negative 1, 0. And then we have 0, 0, 0, 0 for the last row of our matrix. I do want to mention that this is what we call our coefficient matrix. And this vector here is what we call our solution vector. And for the coefficient matrix, we call that A, coefficient matrix A. And for our solution vector, we call that vector X. And then here we have what we call the vector of derivatives. And we will call that the X prime vector. So as you can see, we now know that our matrix formulation of our system would be that the vector of derivatives is equal to our coefficient matrix multiplied by our solution vector. Okay, let's take a look at our next example. Again, we're going to express the given system of differential equations in matrix notation. Let's just start with our vector of derivatives, and we have x, y, and we'll have the derivative. And now we'll come up with our matrix, coefficient matrix. So we have the sine of t, we have e to the t, cosine of t, and a plus bt cubed, all multiplied by our solution vector xy. Okay, let's take a look at our next example. We have a higher order differential equation. This came from our damped mass spring oscillator equation, and we are going to express this differential equation as a matrix system in normal form. So we do need to express, so we must express y double prime in terms of y prime, or of the first derivative. To rewrite the equation as a first order system. So let's do that. So here we're going to let y prime be denoted by v. So let's let y prime equal v. And there we can rewrite the equation as m v prime plus bv plus ky is equal to 0. And then we can also solve for v prime, and we can say that's equal to the opposite of k over m y minus b over m V. So now let's go ahead and express this right-hand side of each equation as a dot product. So now we can see that we can put our system in normal form and express that system. And I'm going to rewrite that system right here. So we have y prime equals v, and we have v prime equals the opposite of k over my minus b over mv. And that leads us to our vector of derivatives. Yv prime is equal to 0, 1, negative k over m, the opposite of b over m, multiplied by the vector yv. Okay, let's look at our next example. Legendre's equation. So in general, it's customary to write an nth order linear differential equation as an equivalent system in normal form, and we define the first n minus 1 derivatives of y, including y, which is going to be the 0th derivative. And so basically what we do is we let x1 of t equal y of t, and so on and so forth. So we will then have x2 of t equal y prime of 2. And you can continue on this fashion all the way to the n minus 1th derivative, okay? So let me just put this, we will use this method to define the first n minus 1 derivatives of y. Okay, so let's continue with what we have here. x1 prime is equal to x2. So now we have a system where we can write x2 1 minus t squared x2 prime minus 2t x2 plus 2 x1 is equal to 0. So that system we can write as x1 prime equals x2, and now we can have x2 prime, solving for that second equation, as 2 divided by 1 minus t squared x1 plus, and that should be a negative, plus 2t divided by 1 minus t squared x2. And that leads us to our matrix system in normal form as x1, x2, there is our vector of derivatives, equal to 0, and I'm going to give myself some room here, negative 2 divided by 1 minus t squared, and then we have 1, and then we have 2 divided by 1 minus t squared. So there's our 2 by 2 matrix multiplied by the vector x1, x2. Okay, let's go ahead and look at this next example, and we are going to express our system as a matrix system in normal form. Go ahead and introduce our auxiliary variables again. So we will have x1 equal to x sub 2 equal to x prime, x sub 3 equal to y, and x sub 4 equal to y prime. So we will rewrite this system as x1 prime is equal to x sub 2. That's our variable we introduced. So that first equation is x sub 2 prime plus 3x1 plus 2x sub 3 is equal to 0. And then we have our next auxiliary variable, x sub 3 prime is equal to x sub 4. And we have x sub 4 prime minus 2x sub 1 is equal to 0. Now, we can go ahead and say that x sub 1 prime is equal to x sub 2. X sub 2 prime is equal to negative 3x sub 1 minus 2x sub 3. X sub 3 prime is x sub 4. And x sub 4 prime is 2x sub 1. So now we have our matrix form as our derivative vector and here's our 4 by 4 matrix. And then here is our solution vector. Let's try that one more time with our next example. So we will introduce our auxiliary variables. So we have x sub 1 is equal to x. X sub 2 is equal to x prime. X sub 3 is equal to y, and x sub 4 is equal to y prime. And we will need x sub 5. Since you can see here we have a y triple. Y double. So that is n minus 1 derivatives that we define. So let's continue on. We'll rewrite this system as x sub 1 prime is equal to x sub 2. That was our first auxiliary variable. Rewriting that first equation as x sub 2 prime equal to the cosine of t, x sub 1 plus 3 x sub 2 minus t squared x sub 3. Here's our third auxiliary variable, x sub 3 prime is equal to x sub 4. X sub 4 prime is equal to x sub 5. And x sub 5 prime is equal to the opposite of e to the t, x sub 1 plus t x sub 2. This is our second equation, minus x sub 4, minus x sub 5. So with that, we can now write our system with our derivative vector x sub 1, x sub 2, x sub 3, x sub 4, and x sub 5 prime is equal to, and now we will have our coefficient matrix. So we will have 0 cosine of t, and so on and so forth. and then our solution vector. And there we have our matrix system in normal form. And that concludes this video.